hopefully you can see me because I have a really janky ass camera setup and I actually can't see myself at all right. But, you know, I'm sure I look so incredible and amazing. As always, I have a really janky camera setup, but I'm just gonna do what I remember doing in class. Oh my god, Pratika responded. Thanks, PB, for telling me whatever we missed in class. But I'm still just gonna do what I remember. Anyways, we're gonna go up here. And I'm coming to the conclusion that I don't think you can read my writing very well from that height, but you can read it like 50%. And honestly, that's good enough for me because I'm not buying a Canon G7X. Basically, the main thing that we covered, let's see, first thing that we covered, yeah, we're talking about geometric, right? This whole like representing functions by power series page, right? Okay, so the main thing that we want to recognize here, hopefully you can still see this, is that before we realize that this series, AR to the n equals 0, and then it converges up to infinity, we realized that this thing converges. Or this thing converges when, at the very least, when whatever your value of r is less than 1, right? So the other thing that we need to realize is that we know the sum for this. We know that s equals a over 1 minus r. That's like basically the only sum that we learned to take in the entire unit last unit, except for telescopic. Unless there's one that I'm just not remembering at all, which is actually like very likely. But point is, this is the only one I remember, and I'm the only important person in the world, so that's all we care about. The point is that we know now how to go from this value, or we know how to go to this function, we could call it. You get where I'm going with this. And we can switch between that and a series, right? Because we've been learning how to do this whole like Taylor series, this Maclaurin series, stuff like that, where we learn how to convert from a function like f of x to a summation. But we already actually know one way to do this. So then this is kind of like a shortcut when we don't feel like writing out the entire Taylor series thing. So if they give us a function in terms of, well, normally, right, when we're doing this geometric thing that we're talking about in class, then they want us to do, like, they give us a couple values. We know what a is, we know what r is, like there's no variables in here. Like they'll be like, oh, your first term is 2, and then you plug in 1 for the formula, and then you're like, oh, and then your ratio is 1/3, and what do you know? That converges. But now we want to see if we plug in a variable here, right? Because a function's not going to be a solid number. I wish it just was. But our function's going to have variables in it. So we're going to look at whatever we did in the notes packet, which looks like, let's just do this one. Okay, so if they give us something that kind of resembles this, let's say, what did I write? 2 over 1 minus x. That's crazy. The things that I just explained for a minute straight, those things kind of match up. So now if I get a question, right, that asks me to rewrite this as a sum, I already know kind of how to convert back. I just do the same thing. I go from here to here, but in reverse, right? So I have this one part of the formula. That's perfect, right? Great, awesome. That's just part of the formula. I know this top one is going to be my first digit. I really hope you guys can read this, but you know what? Survival of the fittest. We have Darwin for a reason. So our first term is going to be 2, which is also going to be our a value if n equals 0. And then our a is whatever's down here. And keep in mind the minus is just a part of the formula. So this is going to be x, right? So x to the power of n. And if we look right here, our r, what would normally be r right here, is right now x. So we need, if x is less than 1, then we converge. or the absolute value. That's crazy. Now we have our super great interval of convergence. We know it's from -1 to 1 because the question told us that it was centered at 0. So now we can really simply do this, and we don't even need to check the endpoints with this, because the great thing is that we know with the R test that if R is less than 1, or if X in this case is less than 1, it'll converge. If it's equal to 1, it won't converge, or at least it's indeterminate, or it won't converge. But so that's how we deal with a problem like this. Another thing that we realize is that we can manipulate equations, right? Just like, you know, like the women at this school be getting manipulated by men who look like rats, you know? So we're gonna start with, let's see the equation. 1 divided by 1 plus x. And I'm not just crazy, because we can manipulate this into having a over 1 minus something. The important thing to realize is the only important part of this formula, a equals 1 minus r. The only important part is that this 1 minus stays the same. So we can just rewrite it as anything, as long as we have 1 minus in there. So let's say our first term can stay a. We don't need to like multiply or divide any of the terms by anything, but we can rewrite this as 1 minus negative x squared. And when we realize, okay, let's convert to writing that as a sum or a series, right? So our first term, our a, what's at the top in this equation, this top is 1. I didn't need to write that, but the bottom of our equation, what we have right here for r, is negative x squared. And we're going to put that whole thing, because it's a geometric series, and we're just following the formula to the power of n. So this whole sum is going to be equal to this right here. We can convert. Let's do a super awesome thing, and let's find the interval of convergence. The interval of convergence is going to be whenever the absolute value of negative x squared is less than 1. And that is going to be, shocker, shocker, that's just going to be from -1 to 1. Okay, super awesome, super great. I actually think there was something else important to do here, but I don't really remember it. So we're actually just gonna, you know, like roll with it. So we're just gonna move on. Let's see. The other important thing that sometimes we have to do, okay, is sometimes we're going to be centered at different values than we're used to doing, right? So they give us this equation on the next page of the packet. F of x is equal to 4 divided by 2x minus 1. Okay, it's a fraction, but besides that, it doesn't look like we really have anything in common with this. So we're gonna rearrange it, right? We don't care what the a is, but we do care there needs to be a positive 1 minus another number. So let's see. We have a 1 here. We can rewrite, if we multiply this whole thing by -1, multiply the bottom by -1, multiply the top by -1, we get the same number, but we can rewrite -4 over 1 minus 2x, right? Right. And then beyond that, let's see. Oh, yeah. We're doing this, though, the reason that this equation is really special and it's not like the other girls is because we're trying centering at c is equal to 2. And so instead of just rewriting normally, right, if it's centered at 0, so it's like, say, a Maclaurin series, then we could just take this guy and we could be like, cool, that's our r, this top one is our a. Like we're super great. Everything's awesome, right? But we have to be special. We have to have c is equal to 2, okay? Which means that we need to include parentheses x minus c somewhere in there. X minus 2. Because that is just how Taylor polynomials work. Like, let's think about it like this, right? Let's say, whatever. If we have a sum, right? Starting at n equals 0 of 4 times, let's see, x minus 2 to the power of n, right? So if this is going to be our sum here, then what we could realize is that for every single value of n, except for n equals 0, so if like n n can be like anything in the entire world, right? If we are at the value of 2, then we are going to just get 0. So let me actually rewrite this. So we said c is equal to 0, so let's rewrite this equation at the center. If we're rewriting at the center, then we're going to have 4 times 0 to the power of n. So if we rewrite that as our first, second, third, fourth in terms of the series, our first term is going to be 4 times 0 to the 0, right? And then we'll add on all our second terms. 0 to the power of 0 is equal to 1. But all the rest of these are going to be 4 times 0 to the 1, 4 times 0 to the 2, 4 times 0 to the 3. That just adds up to being 0. So essentially, we're going to get this like really convoluted point where at the center, the sum is going to be this whole a thing. At the center, it's going to be whatever your first term is, which is the value of the function. But if that seemed really confusing to you and really annoying and really awful, Loki, you could just ignore all of what I just said. If you only memorize how to plug and chug this and you don't understand like the actual mechanics behind why we include x minus 2 in the function, girl, you'll still pass the test. No one really cares. My point is, I'm going to show you how to take this function, right? And we're going to rewrite it to include x minus 2 in it. So let's see. We could rewrite x as x minus 2 plus 2, right? Same difference, but we added more numbers just for funsies, I guess. So we're gonna try doing this over here and see how that works out. So we're gonna start with -4 at the top because that doesn't change, divided by 1 minus 2. Cool. Now I've successfully written this at the top as this down here. I'm really hoping you could read at least one of those things, because again, I can't see anything that's going on. So if this is the case, then you could distributive property things out, right? And it's going to be a massive pain, because these kind of questions are. You're going to end up getting -4 over 1 minus 2 times 2, 4. And then you're going to get minus 2 times x to the -2. Right, we just factored out to this and this, right? So we could keep this in here as a term. -4 over, we're going to simplify these two guys, -3 minus 2 x minus 2. Wow, super great. And joy only is like needing the Heimlich maneuver at least one time. Now you're gonna say, Joy, this looks really ugly. Nobody wants to solve this equation. Suddenly, this doesn't even look like the original formula again. So if you see something that says like centered at x at c equals 2, you're gonna rewrite an equation that looks just like this, right? And then you can just substitute it in step 1. Because what happens is you need to do the annoying rearranging thing anyways, right? So then you need to do that thing. You want to get this value down. You want this value has to be 1, positive 1 for the formula to work. And then everything else, we don't care. A could be whatever, R can be whatever, anything else can be whatever. So I'm going to multiply all this by -1, because that's how I get from this negative to positive, right? I'm not even going to rewrite this. multiply by -1, everything becomes positive, right? But that still hasn't really done that much for us. So we're gonna end up dividing the numerator and denominator by 2. This is 4/3, 1, I just divided everything in here by 3. And now we've got this super great 1 minus. 1 minus means, cool, the formula works. This matches the sum formula. And what I've done here is I just divide this term by 3 as well. Right? Divided it by 3, and this just becomes a coefficient of 2/3. The other thing I did that you might notice is I swapped this around so we have the negative in here, because again, it has to be 1 minus. 1 minus is the whole reason that our formula works. Okay, that's super awesome. That's super great. Now we have to actually do the thing, right? So they might want us to find the interval of convergence, for example. So we know that this is equal because now that we have the geometric sum formula, we can easily convert. We can easily convert from f of x, which is this ugly equation, to our beautiful, super gorgeous, this one actually is going to be pretty ugly, but our conceptually beautiful sum way to say the things. So this top thing is a, so it's going to come first. That's how the formulas work, crazy work, and all that jazz. This is going to be -2/3. You can't see that 3, so I'm going to rewrite it. -2/3 times x minus 2 to the power of n. Isn't she gorgeous? Isn't she so pretty? So we're going to, now that we've done that whole thing, we can confirm that it's centered at x equals 2, because we know we have this x minus 2 term in here, right? So we can confirm that she's centered right here. But now they're going to ask us for the interval of convergence. And what this was supposed to do was help us save time. So we know that the interval of convergence is going to be whenever this r is less than 1. So we're just going to solve for when -2/3 x minus 2 is less than 1, which then you're just going to do some algebra. It's going to be a whole thing. Solve algebra, whatever. What you end up getting is your endpoints are -3/2 and -2. Those are the two values for which this inequality links up, right? Now you have the interval for convergence of this equation here. Wasn't that so simple? Wasn't that so easy? Now we're super happy and we're super excited because now we get to move on to using trig in our equations. You guys are welcome. Also, I don't have scratch paper, so you're gonna get like 30 seconds of silence and ASMR noises because I am looking for her. Let's do the great thing where we can involve trig into the equation. So like the main example that they're ever going to care about is going to be, let's see, they're going to care about this thing called Gregory's series, which is so specific, and the fact they dedicate an entire example to this, I wouldn't be super surprised if this is on the quiz. And that is, they say, f of x is equal to arctan of x, right? Find a series for it. Okay, and like your first instinct might be to plug in, right? Oh, and this is centered at c equals 0, which looks like nothing at all. And then your first instinct might be like, okay, let's do the whole Taylor series thing where we're gonna have like f, the nth derivative of x times x to the power of n over n factorial. But that becomes really annoying because then you have to know what f to the nth derivative is, and then you have to keep deriving arctangent a billion times, and then you don't really have a great answer for that. You don't really have like a great super neat way to write that out. So instead, we're going to rewrite arctangent instead of just trying to blindly plug this into the formula, right? So arctangent, we know, is also equal to the integral of 1 over x squared, right? And wait, or 1 over 1 plus x squared. Aren't you guys so glad you trusted me with your education? Arctangent is also equal to this guy right here. And then what we realize here is that this little thing kind of matches that super sexy, super gorgeous sum equal to a over 1 minus r formula from before, right? So we could finesse this thing. We could work that out, right? So we're going to rewrite this as the integral of whatever our other way to write this thing is, right? And what we realize is we did this before, right? So you know how to rewrite this as a series. You know how to involve a series in here. We did this whole thing where we started with this guy, right? And then we figured out that we can flip the sign in this to make this negative and fit the formula. So this right here is r, this right here is a, this right here is r, and we can create this gorgeous, sexy, amazing, beautiful thing, right? We're gonna do that again. So now we can plug this in. We're gonna plug this in place of this, because like these two are fundamentally equal. So this is gonna be negative x squared to the power of n. And then, so the Gregory series is what we're doing. The other super cute, great thing is now we have to take the integral of this entire series, right? Which actually does look awful until you realize that this actually isn't that bad. So to take the integral of this, right, this thing in here is kind of ugly. No one really wants to deal with that. So we're going to factor this into -1 times x squared to the power of n, right? And what that allows us to do is get rid of that super nasty, super ugly negative exponent. We want to get rid of the negative in there, right? So then we can distribute this exponent into here. So then that becomes -1 to the power of n times x to the power of 2n, which we know because exponent rules that we definitely all remember from pre-calculus and whatever class that was, right? And now we can take the integral of this so much more easier, right? So we're gonna write, let's take the integral of this thing. What we realize is that for any value of n, right, this is a constant. We're gonna do this like at a million different times. I'm mostly explaining this for the benefit of Tanushi, but here's a refresher for everyone else as well, because she missed a day on integrating and deriving these things, is that, let's see, oh yeah, we're gonna value this, when we have a sum, they're valuing this at n equals 1, n equals 0, n equals 2, n equals 3, all those values, right? So then anything with only an n in it is basically gonna become a constant. N is always known. So this whole thing, this part simplifies out to a constant, like even like n itself right here simplifies out to a constant. We just have to integrate the part with x in it. So we're gonna integrate, right? This -1 to the power of n, that's just a constant, and that stays whether we integrate it or not. And then I hope this thing is still recording. We're gonna take our integral formula, which is gonna put, we can raise this power up by 1. And then we divide by the power raised up by 1. Oh, I love how I just crossed that out. I'm gonna rewrite that the exact same thing, except without me crossing anything out. And that is how we write arctangent of x as a series. And this is what your calculator is doing every single time, because it's really dumb and this is the easier way for it to do it. So to recap, you will start by rewriting this arctangent as this little fraction here, and from the fraction you can turn it into a series, which you just then integrate. That's super great. I hope this video isn't too long. Let's see. Oh, she's 26 minutes. But like all of y'all's attention span is like terrible anyway, so I'm sure that you can just put it in 2 times speed. You're welcome for the really concise explanations. I really try to give those all the time. You know, I'm really doing the Lord's work here and all that other jazz. You guys are welcome for my existence. Okay, bye.